what we would like to do now is, rederive, particularize this integral and solve it. But no, we have to do some math. Okay. And now, for Gaussian process, we would like to simplify this integral, actually compute it, but we need the probability structure of for a Gaussian process. Okay, what is the probability structure? So let's define. In our case, in general, if we have a list of random variables x, okay, which in our case is what? In our case, basically, is eta naught, which is the process at eta t naught, and its derivative eta t naught equal the derivative at t naught. Okay, this is, we have our list of random variables. The probability density, the joint probability density function of px is equal to, in general, 1 over 2 pi n divided by 2 square root of the determinant of the covariance matrix exponential of minus 1/2 x transpose the inverse of the covariance matrix times x. Okay, so this is the joint PDF of x. Okay, so what is in this case the covariance? The covariance matrix gamma is the covariance matrix is equal to, in our case, it's going to be simply eta t naught squared average, eta t naught, eta dot t naught average. Here we have the same, eta t naught dot average, and here I have eta dot t naught square average. Okay, I'm going to show that this covariance matrix is basically equal to m naught 0, 0, and 2 is diagonal, and here basically I define the spectral moments m sub j as the integral between 0 and infinity of s of omega j, omega power of j in the omega. Okay, so of course you see that m0 is basically this, the variance. Okay, but the correlation, the covariance matrix in this case, will be, or the correlation in this case is covariance because we already know that the average in general, here the average of x is always 0 for us. Okay, because we were dealing with waves, so we always remove the mean and we want to study fluctuations. So how to show, for example, that these moments are correct? So let me give you an example. Again, we need to go back to our definition. Eta t naught is given by the process n1 to n of an cosine of omega nt plus epsilon n. So quindi, for example, if I want to do eta t naught dot, the first derivative, we already know what it is summation from 1 to n of an omega n minus sine of omega nt plus epsilon n. Okay, so this guy is equal to the double sum n of an, there is a minus am omega n cosine of omega n t naught plus epsilon n sine of omega n t naught plus epsilon n, and then I have to do the average, the statistical average of this guy. But this is equal to minus the sum over n and m of an omega n cosine of omega n t naught plus epsilon n sine of omega n t naught plus epsilon n average. And it's easy to realize that for any n and m, this is basically equal to 0, okay? Because no, I mean, these are going to be stochastically independent. So I can basically do this is equal to cosine of beta n average times cosine of beta n average, okay, which are both equal to 0 and 0, okay. So then we prove this very easily, okay. Then if we want to do the same for the for eta dot square average, is the same stuff, is the double sum n m of what? Of the square of this guy. So it's going to be minus and minus plus a n omega m sine of beta n sine of beta n. Then I have to do the average of this guy, okay. Where basically I define beta n equal omega n to naught plus epsilon n. But now this average is equal to 1/2 only when n is equal to n, and 0 when n is different than n. So the things is going to be equal to the sum over n of an squared divided by 2 omega n squared. But this guy basically is the interval within 0 and infinity of s of omega squared in the omega. So this is the second order moment of the spectrum, okay. And the spectrum, remember that is always given, okay, always given, or you can estimate it from the data. So once you have the spectrum, for Gaussian process, you have the full characterization of all the probabilistic properties. Okay. So said that, we basically saw what we have that x, the x vector is basically eta dot eta t naught, okay, which in and then the probability of x is going to be equal 1 over 2 pi 2 over 2 square root of the determinant of the covariance matrix times exponential of minus 1/2 x transpose. Now we have to do the inverse, which is pretty easy, because we have the covariance matrix is going to be m0 m2 0 0. So the inverse is pretty straightforward in this case, 1 over m0 0 0 1 over m2, okay. So the probability of eta naught and eta dot, which is valid for any t naught, okay, really, I can even remove this index, okay, the process is stationary, so it doesn't depend upon time. It's going to be equal to 1 over 2 pi square root of the determinant of this matrix, which is m0 m2, and then I have exponential of minus 1/2. That's pretty straightforward because it's equal to m0 eta 0 squared plus m2 eta 0 squared. Okay? So actually we see that the processes are independent, because I can split this guy as 1 over square root of 2 pi 1 over square root of m0 times 1 over square root of 2 pi m2. Then here, sorry, I can make exponential of, let me do it again. So this is equal to exponential of minus 1/2 m0 eta 0 squared divided square root of 2 pi m0 times exponential of minus m2 eta 0 squared divided square root of 2 pi m2. So basically these processes are independent. That's what we prove. And because we already know that they are uncorrelated, and for Gaussian process, uncorrelation imply also stochastic independence. But this is only true for Gaussian processes, okay? Because there is no structure there of like in a manifold. So actually this result is pretty nice, because now we're going to use it because we want to compute what the expected number of upcrossing greater than h is equal to 0 to infinity of this of eta naught equal h, eta dot equal w, w dw, but we take advantage of the independence of this process, of the fact that these two variables are stochastically independent. So I have probability of eta naught times probability of eta dot equal w, w dw. Okay. So and we know what are the probabilities of this. The probability of this is this, the probability of this is this, the PDF, so the PDF of this is this, the PDF of this is this. And so basically, let me keep those formulas there, so we will use it later. So I can bring this guy outside the integral, so I will have p of eta equal h, integral between 0 and infinity of p of eta naught w, w dw. And now I can use the results, because this guy is equal to exponential of minus 1/2 m0 h squared divided square root of 2 pi m0 times the integral between 0 and infinity of 1 over square root of 2 pi m2 exponential of minus m2 w squared w dw. Right? And this integral, it's easy to compute, because this integral actually is easy to compute, because it's equal to 1 over square root of 2 pi m2, and then I have e to the minus 1/2 m2 w squared by what, basically? Let's see, 1 over m2 computed between 0 and infinity, but I also need a minus. Right? But indeed, when I take the derivative of this guy, m2 and 2 simplify, so I will end up with I will end up with this extra component, which is going to give me this, which is fine. Now, when omega tend to infinity is going to be 0, omega equals 0, this is going to be plus 1 over m2. So the final result is going to be exponential of minus 1/2 m0 h squared divided square root of 2 pi m0, and then basically these results now is telling me that I have 1 over square root of 2 pi, and then here I think I did I make a mistake here? Yes, I'm sorry, I made a mistake here. This is here I made a mistake. This is wrong. So the m0 goes on the denominator. Sorry, and of course has to go to the denominator. Okay. So let's make sure again that you see this stuff, okay? So because we have 1 over m0, 1 over m2, okay? So and then when we do the correction here, this guy belongs here, m0, and this guy belongs here, as m2, and then when I do this integral now, the m2 is on the denominator, so I need to have m2 on the numerator. so that when I do the simplification, this guy becomes square root of m2 here, and that's it. And so the final formula is going to be ex ut of h equal square root of m2 m0, which equal 2 pi equal 1 over 2 pi exponential of minus h squared divided by 2 m0 squared. Okay? Which is also equal to 1 over 2 pi, let's write it in this way, m2 over m0 exponential of minus h squared divided by 2 m0. That's a very nice result, because now the probability that a crest C is greater than h is equal to what? Expected number of upcrossing of level h times t divided the expected number of zero crossings, equal to 0 now, times t. Basically, this formula is going to be this on the numerator.